Okay, welcome everybody. Good morning. Welcome to the SNCC seminar, number 6. It's the third seminar we are holding here in Geneva in person. So welcome to all the delegates who are present in the room, and of course, a warm welcome to all of you online. And yeah, first of all, let's start with a very short introduction of the seminar. Yeah, can we go back one slide? Just a short note on myself. My name is Hans Walter. I am the chair of the SNCC committee, which is the Spectrum and Network Implementation Committee. I work for a network operator in Italy, which is called WorldDAB Italia. We provide the service to national commercial radio stations. We broadcast 8 stations, additional services, and we have also external customers. You have a short overview of the coverage of Italy and the major station brands. Also, I'm of course the chairman of the SNCC committee, which stands for Spectrum and Network Implementation. And what does the SNCC do actually, this committee? It will provide guidance on regulatory approaches and the introduction on DAB. It lobbies to ensure spectrum. We also give advice on best practice to operators. So if you attend the meetings we have, and if you can also write to us, you can get information on how to build your DAB network, on technical issues, whatever. We are really always happy to support you on all the technical aspects we can provide you. We give advice also on the multiplexing part, on the sound processing. So a lot of members are also manufacturers, so they can provide you insight into the technical aspects. And of course, also on monitoring and all the rest, which is, let's say, connected to the day-to-day management of a national or a local or regional DAB network. And the very important part of this committee is also, it is a platform for exchange of experiences. So when we meet, we try also to ask questions, get answers, and support each other. So please, if you are a WorldDAB member, I suggest you to register to this committee. It's a nice place to be. We had an interesting seminar last year on planning. I suppose many of you attended this seminar. And I really hope that this year we will have a similar successful seminar. We got a lot of takeaways, and I'm really looking forward to get the takeaways of our presenters today. We have a very interesting agenda. We will shortly start with Alexander Kurz, who will talk us about the migration scenario from FM to DAB, followed by Adriano Pitteri from SRG, who will tell us about the switch-off of FM in Switzerland by the public service. We'll have a coffee break then after that. And then we go to the more transmitter-related part. We'll have Luis Grela from Trades, who will illustrate let's say, technical aspects of power consumption and reduction. We have a very interesting presentation from Phil Casby on how Archive and BBC are reducing energy consumption or increasing the efficiency, let's say, of their DAB network. And after lunch, we'll have Carlo Perotta from Aldena, who will have a presentation on antenna systems, on how antennas can, and the correct planning of antenna systems can allow us to reduce, of course, costs and power consumption also. And last but not least, we'll have Justice Appiah from Ghana, who will tell us about how Ghana is running DAB transmitters on solar power and anyway connected off-grid, so not connected to a power network, which is very interesting, I suppose, especially in some areas in the world. Okay, and this takes us to the end of my introduction. Alexander, the stage is yours.
Thank you, Hans. Good morning, everyone in the room. Good morning, everyone online. My name is Alexander Kurz. I'm with Gates Air, and of course, transmitter manufacturer as well. So today the objective is to take a look at the migration from FM to DAB, the efficiency savings, and how we can help you in driving those efficiency savings and the power, using the power more effectively. And as part of my presentation, we will also take a look at what new developments have been over the last 2-3 years to reduce energy consumption even further. So in general, DAB has an advantage when it comes to optimizing spectrum usage. You have multiple channels in one channel, so multiple stations in one channel. You have a crystal clear audio quality, and you can deliver multimedia services like content, weather information, traffic information with maps, covers of CDs of titles. You can tell I'm old school. The operational benefits, very, very clear, are the power consumption. So one of my following slides will speak about how DAB uses a fraction of FM power for the same coverage with the same quality. You have the shared infrastructure. So if you look at multiple FM stations, everyone operating their own station, the DAB consolidates that into a single source, a single transmitter, a single tower. The branding is possible to improve by using metadata and multimedia content. So there are stations who purchase more capacity on a DAB channel to show updated pictures of the studio, for example. You have some multi-tenant capabilities in an SFN network. And finally, the architecture itself is software defined. So you can change what you're transmitting. So one of the most recent developments in the software defined architecture is the introduction of alarming capabilities in DAB, where European broadcasters work together to define alarming capabilities that slowly migrate into the receivers to wake up even if they are turned off, and allowing you to alert the population. So very specifically, if you compare a typical installation of FM and DAB, so one DAB channel can handle typically 18 programs. It's a little bit a question of quality that you have. If you use those 18 channels in a very high quality, maybe then you're down to 16 or 14. If you have some talk radio in there, you're at 18. And all of that can be handled by one transmitter. In FM, you would need the equivalent number of transmitters. So instead of one transmitter, you have 18 transmitters. In DAB, of course, it all goes on one frequency, 1.5 megahertz in the VHF band. In many countries, VHF is underused because television mostly is in UHF. So you have no frequency problems, no channel problems. Whereas in FM, you would need 18 frequencies, especially in larger cities. Think about Istanbul, because I see my Turkish colleagues here. There is, I don't know, 16 million people and dozens of radio stations. You cannot get new frequencies in these large places. So you move into the DAB for more frequencies. Of course, license fees are a topic. You have to pay for each license individually. The connection, how to get your audio signal from the studio to the transmitter, you need individual studio to transmitter links to distribute the signal. In DAB, it's one versus multiple. The data information that is included in RDS, for example, traffic information, alternate frequencies, title, and artist, you have to deliver multiple times. You need multiple RDS encoders in FM. In DAB, you provide the data once to the DAB multiplex and then can play it out. And of course, the antenna is a big factor as well. For 18 stations, you need antenna capability for 180 kilowatt if you have a 10 kilowatt system. In DAB, you need one medium level antenna, which brings me to the next slide, which is talking about the cost efficiency. The cost for, let's start again. The coverage that you achieve with a 10 kilowatt transmitter is approximately the same as you can achieve with a 2.5 kilowatt transmitter from a power level. This means based on the AC to RF efficiency, you need a certain amount of power, and that certain amount of power over the duration of a year results in the annual energy cost that you see in the last line, and that's a staggering difference. Now, keep in mind that the AC to RF efficiency, both numbers are conservative. So 72% was what used to be FM efficiency up to 2 years ago. Now we speak 76% roughly. For DAB, 40% was state of art a couple of years ago. Now we speak 45 to 50%, depending on a couple of parameters I'm going to come into in a few minutes. So, and the cost, of course, are based on 15 cents per kilowatt hour, in this case, US dollars. Now, depending on your own energy prices, you can do the calculation yourself, but the relations stay the same. So even if the efficiencies are increasing, it's a multitude of energy costs in FM compared to DAB. Oops. Now, how do I come to those numbers? And that's the part with, if you compare DAB with FM, you need 10 times less RF power in the field. But at the same time, you have higher losses in VHF because you're in a higher frequency band. So the effective transmitter power is about 1/4. So instead of 10%, you need 25%. But it'll result in about the same coverage area. Now, of course, and where is Carlo? He will speak about antenna and how to use antennas to gain efficiency. So the antenna gain has a little influence here as well. And that may unbalance or balance this a little bit. So, as I said, we're a transmitter manufacturer, so we do offer a relatively wide range of different transmitters, from very low power in the ultra compact form factor that's up to about 700 watt to well over 10 kilowatt in the OP series. We have solutions that allow you to have multiple DAB transmitters or multiple DAB multiplexes in one transmitter, so you can save on the combiners, on the other equipment. That's a very good solution if you have adjacent or closely positioned frequencies. And then we have a solution that is a compact transmitter for outdoor usage. That's a little gray box in the right. And of course, we have some liquid cooled systems as well, as you see with a ventilation system. Now, I don't want to speak too much about what we do, but one reference for it is that Saudi Arabia recently started rolling out transmitters into the main locations, the main cities, and the main highways. So that's happening as we speak. They have installed, I think, about a dozen right now. The final build out is about 60 transmitters along all major highways in Saudi Arabia in all the major cities. The efficiency increases, and that's a thing that we will hear more about from further speakers, Phil and Luis, but the use of new transistor types allows us to increase the efficiency between 5 and 10%. That very much depends on the specific transmitter level. So we see significant increases in the lowest power levels, because here the transistor or the efficiency of the amplifier has a large influence. And that's rolling out over the course of this year. The other aspect, and here Phil from Arqiva will speak later on, is that you can increase the efficiency of a transmitter by reducing MER. So reducing the quality of the signal at the transmitter allows you to have a higher efficiency. This is an indirect relationship. So if the efficiency goes up, your MER goes down. Now, there are studies that show that reducing MER has a minor impact on coverage. I have to say that there are other customers of ours who believe the highest MER is the best. Others say, oh, it doesn't matter that much. So I would say, sorry for that, but the jury is obviously still out. And we help everybody to do it as they want. So the way how this is being implemented typically is that you vary the voltage that comes out of the power supply unit into the transmitter, into the power amplifier. So you increase the voltage or you decrease the voltage. That has a direct influence on MER and efficiency. You see the numbers. We speak about a couple % in efficiency. Now, keep in mind, we're already talking high efficiency already. That pushes the efficiency above the 50% level. So a couple minutes ago, I spoke about 50%, I spoke about 40% efficiency. In the very low power, that's even below that. Now we are speaking 45 to 50%. Now keep in mind, those are peak values in certain channels. On average, those numbers are typically 1, 2, 3% lower. And again, this is a development that is being implemented as we speak. So the final numbers will come out over the course of the coming months. For everybody who is planning transmitters, we have certain considerations that I would put out for consideration. I understand that customers or listeners in this audience want to know how to roll it out. Redundancy concept, how reliable, how resilient do you want your transmitter network? So between single drive, dual drive, and complete 1+1 redundancy, of course, you have higher reliability, higher fail-safe systems. And then we have what we call a power supply redundancy. You see in the lowest picture, we use 3 power supplies. If one fails, you still have 100% reliable output power. I have seen this with other vendors as well, so it seems to be a concept that's been taken up. Previously, redundancy in power supply meant the 1+1, so 1 active, 1 reserve. Now with this, you can do it a little bit more cost efficient, achieving the same result. Now, this is also important because you can connect each power supply to a phase of incoming 3-phase system. So even if the outside world only delivers 2 phases to you, you're still 100% on the air. Other considerations, of course, output power. You typically calculate back from the dB microvolt you have on air, antenna gain, losses in the RF feeder, losses in the combiner, respectively in the mask filter. Then you end up at the output, what you need on the transmitter. And you get the field strength from a coverage study your friendly antenna provider or consultant will provide you with. Efficiency, spoke about the MER relationship. keep in mind that Doherty versus Class AB amplifiers and the power amplifier has a big influence, even at low powers. So we recommend to consider as low as possible. Input options, if you roll it out, when it comes to efficiency, you have to get the signal somehow to your transmitter. Satellite is a popular or has been a popular distribution method. I'm just looking here at my friends from WorldDAB Italia who used that for a long time. Nowadays, EDI, which is basically IP distribution, is happening. And spoke about air cooling, liquid cooling, and something that's sometimes overlooked, transmitters can be optimized for a narrow bandwidth or for a wide bandwidth. There are advantages to each solution. If you have a narrow bandwidth, you typically have a better efficiency and more linearity. If you have a wider range, you can tune the transmitter easily. Now, again, it's you have to balance this off. So, concluding, Gates Air has been in the DAB plus and DAB transmitter business for 25 years at least, maybe even more. We are targeting and improving our products for efficiency, scalability, and cost effectiveness. So total cost of ownership is a critical element in here. The deployments we are rolled out European-wide in DAB plus in Australia and other parts of the world. And that's basically the end of my presentation. Thank you very much. Contact details, and I think I hand over to...
I would like just to add some words. Thank you, Alexander. Any questions you have, you're really invited to save them for the Q&A session at the end of the seminar. You can send them on the Zoom or hand them over to me and Michelle here in the meeting room. So yes, that was everything. So if you have any questions for Alexander, write them down and we will ask him later and have a nice discussion. So now the floor is yours, Adriano. Thank you very much.
Thank you, Hans. Thank you. Welcome here in Geneva. And I'm really happy to be here with you and also online inviting you here in Geneva because it was here that all began of my passion of radio and the discovery of all the possibility that radio brings. And after creating different radio program and dreaming a digital future of the radio, I'm really happy now to be here and to present to you a milestone that the Switzerland achieved in the radio history by the switching of the FM. My name is Adriano Piteri, and I'm responsible for the broadcast distribution at the SRG SSR, that's Switzerland's leading public media service. Some words about the SRG. We are an association, politically independent, and providing the biggest public service media in Switzerland. We run 17 radio stations and 7 TV channels for the Switzerland's 4 linguistic region. And for this, we are about 7,000 employees doing this big job. Switzerland is, of course, known for its famous quality of life and the beautiful mountains, like here on this picture. But what recently put Switzerland in the headline was the FM switch off that the public service and some private radio station performed at the end of last year. How we came to this and all the transition from FM to DAB+ took a few years in Switzerland. The beginning was in 1999, where we commissioned our first DAB transmitter. In the early 2000s, private radio stations spoke of the need to obtain new frequencies as the FM band was saturated, especially also because of its proximity with the neighboring countries here. In 2008 and 2010, we switched off our main two middle wave transmitter and launched DAB+. But a key moment in the transition to DAB+ was 2014, where the entire radio industry agreed on a common roadmap for the switch off of FM between 2020 and 2024. And since 2020, DAB has become the main and also the reference medium for radio broadcasting in Switzerland. And as I said earlier, by end of last year, the public service and some private radio switched off their FM transmitter. But what's most remarkable is the joint work between all the players in the radio industry. And this was really the success. This enabled everyone to participate and get involved in this process of switch over to the digital radio. And as a result, we have been able to successfully carry out several campaigns to promote DAB+ at the first instance and to inform people to the switch off in the second. And so we are here today. That it remains the end of the FM licenses for the private radio in Switzerland that will be at the end of 2026. Perhaps why did the SRG switched off already in 2024, so last year? The different points. One is the SRG faced that from the outset that the DAB will be the future of the radio, the digital future. And so after more than 15 years of simultaneous broadcasting between FM and DAB+, it was time to finalize this replacement. The DAB coverage is excellent, far over 99% of the population coverage. And the DAB coverage is also far better than the FM, with plenty of new extra programs. And the SRG is also a reference for the emergencies as public service media, and our main DAB transmitter and also the routing system are supplied with emergency power up to 10 days. And this coverage can also be increased by providing a higher protection level, for example, with EEP1A. Another reason for the switch off was the money, because in view of the financial situation of the SRG due to declining advertisement and revenue and inflation, the further investment in outdating technology was no longer justifiable. And the digital usage was really good with the DAB and the IP, so internet. We have two digital reception options that offer better sound quality and a greater program selection, and are more energy and cost efficient and provide additional information. And this the user behavior shows also that the majority of the population is already using the digital option with over 80% of digital listening, and the FM only listener are less than 8% in Switzerland by end of last year. And truth, with the FM switch off of the SRG, it's also supporting the private radios that are more dependent on the advertising to do the switch off later on at the end of 2026 at the latest. Here, some graphical view also from the digital radio development in Switzerland. You see that the digital radio consumption has grown steadily since the roadmap was announced in 2014, reaching 83% of digital listening at the end of last year. And in this summer, we will have the next figure of the usage. Yes, Switzerland speaks 4 languages. That's why we had the 4-language campaign for the switch off in Switzerland. All the information you find also on dabplus.ch, who did all the campaign for all the radio industry in Switzerland. And this campaign was a really big success. We had a large information campaign in the last month before the switch off. This helped a lot to inform the people, and we did also specific information only for the FM on the FM channel to be sure that perhaps people that have an DAB radio but are listening in FM, that they be aware to switch the reception mode and listening on DAB. We had the winter tire effect as expected. So in Switzerland, when it comes to snow, you need to change your tire. And a lot of people are waiting the first snow to realize, oh, I need to change my tire. And that was exactly the same with the FM switch off. Everyone was informed with a huge campaign, but I hear also from friends of mine that really waited the 1st of January to change and buy a new radio. A success factor for us was also less reaction. We had all the support information everywhere with a telephone, email, and so on. But I think with the huge information campaign, all the people had all the information needed to know how to equip, for example, for the car or at home, and this was also a big success. And the next usage figures are coming out in the next weeks or months. I think in July we will have some stabilized numbers to see how was definitely the migration. But until now it was really excellent, and we're really happy with them. So now, ready for the run between FM and DAB+, and a little comparison between our networks of FM and DAB+ for the public broadcaster in Switzerland. So if you're looking on the program level, we had about 4 programs in each region that were available on FM. With DAB+, we have 16 programs per layer. In Switzerland, we have different layer, but this is for the public broadcaster layer. If we look on the transmitter number, we had over 850 transmitter for the FM for our programs, and in DAB+, we need only 260 transmitter to cover, as I said, 16 programs. But my preferred number, and it's bring all together, is the population coverage. With the FM, we had about 95% of population coverage, and with DAB, we have achieved 99.7% of population coverage, and this in portable indoor with 61 dB microvolt per meter. So also with a strong field strength, and this field strength we increase it also in the cities to be sure that the coverage is also better. So with all this together, we had really an clear way to decide that the DAB is clearly more efficient in our view, and that's why we decided also to switch off FM last year. Here also a visual presentation. You see the 4 linguistic regions in Switzerland and all the programs that have a little red button. There are all the new programs that wasn't available before on FM. So we gain also a huge amount of program and content variety thanks to the DAB+. And to finish with a nice view also of our mountains, we're really happy that our provider, or the network operator, the Swisscom Broadcast, is also putting some solar energy on the transmitter sites, and so support a part of the energy consumption of our DAB network. So that was my presentation. Some key points. And last year, the public broadcaster switched off successfully the FM. In end of 26, we have the end of the FM licenses in Switzerland. DAB is clearly more efficient. And I want to point out, and this also for you and your experience in the other countries who plan and switch over or an increase of the DAB, is the importance of the collaboration across the radio industry. It's between the regulator, the broadcaster, private and public, the retail, the car industry. So everyone sit together, talk together, exchange your needs, and your plans to so successfully do the migration together. And the DAB is clearly for us the future of the digital broadcasting. Thank you very much. If you have any question, with pleasure, email or after in the panel.
So, hello everybody, welcome back to the second part of our seminar. And let me introduce Luis Grela from TREDES, who will give us a presentation about transmitter efficiency and how to improve, let's say, the energy efficiency at the transmitter side. So please, Luis, the stage is yours.
Hello, thanks Hans for the introduction. And yes, hello everyone. My name is Luis Grela. I'm representing the Spanish company TREDES, and for the next 15 or 20 minutes, the idea is try to share some ideas of how we, the transmitter manufacturers, can really help on contributing to save some energy consumption on DAB+ networks, okay? So although quite a large number of the WorldDAB members already know us due to collaborations we have been doing together, I will start with a very brief introduction for whoever does not really know us well, and then we will focus on the, let's say, core topic of the presentation, that is how we can optimize energy on a transmitting side and try to get to some conclusions, okay? TREDES, we are a Spanish transmitter manufacturer, fully specialized on air-cooled transmitters for TV and DAB+ networks, and we count with around 28,000 transmitters on the field in more than 65 countries, okay? Our portfolio covers from very low powers up to whatever maximum power a network operator wants to run in air-cooled, let's say 5 kilowatt, that we have been delivering air-cooled transmitters. And it has been in the last 3 to 4 years where we have really become an important player in DAB rollouts, counting with around 500 DAB+ transmitters deployed in more than 15 countries, okay? We became a member of the WorldDAB quite recently, earlier this year, so quite pleased of being participating in this seminar and yesterday's meetings. So very happy of our participation in this group. This is the typical panel of let's say, projects or countries where we have been deploying our solutions, and some of the names you see there are already members of the group, so they are already knowing our solutions quite well. Yeah. This is a global map giving an idea of our, let's say, presence in worldwide, especially in Europe. So we have a very large footprint of transmitters deployed in many, many countries. Not so much in the very higher powers, but in the medium to lower powers, we are quite powerful in helping network operators to really achieve their target coverage they really want, okay? In terms of portfolio, we will focus today on the DAB plus area, but I mean, we cover TV transmitters in multiple standards, 5G broadcast as well. And as Alex was mentioning earlier in the conversation, we have lower power units and medium power units or higher powers. Lower power units are trying to focus on trying to make some compact devices with all the exciters and amplifiers embedded into the same chassis. Medium power is typical architecture with a separate exciter and next number of amplifiers. And all this is completed with auxiliary devices type of multi-band, multi-constellation, GNSS receivers, media converters, satellite receivers, and so on, okay? Just to finalize introduction, just random pictures about projects that we have delivered in lower power on the left, medium power of 2.5 kilowatts in the right-hand side, a 5 kilowatt transmitter in a single rack, and multiple 5 kilowatt transmitters in this picture, okay? In terms of DAB projects, this number of 500 comes from multiple type of cases, okay? So we have been participating in new phases of deployment of existing countries, further extension of the countries who are really having already a quite advanced coverage, others who are already starting, and there is also a relevant amount of devices that are being, let's say, renewed. And efficiency is probably the parameter that has been driven that kind of renewal, okay? So the same that happens to GatesAir and to us, in order to be participating in all those projects, you are forced to be up to date with the latest possible technologies, okay? And from our end, the idea is always to be with the highest possible efficiency that the technology allows. And nowadays, really, this can really bring efficiencies into the level of 50% or even a little bit higher. As Alex was mentioning in the morning, we are stating 53 because that's a real number we can measure into our existing transmitters, okay? Also, another way of helping the industries to bring higher performance DAB plus SFN gap fillers to cover gaps in a much easier way, okay? We will go through that now, okay? So going into the core of the presentation, I will start trying to give an overview of how internally we can really improve the efficiency of a transmitter, and then to come into some other aspects that really can help also from getting better efficiency figures on a transmitting side, okay? So when we think about efficiency, the first word that needs to come to our mind is Doherty technology, okay? That really became as a standard nowadays. But I would like just to do a couple of remarks on this. First is the benefits of having like a wideband Doherty technology, meaning that in the end, you are using the same amplifier for the entire DAB plus band, okay? What makes a much easier operation, configuration, maintenance, and optimizing also the number of spares. And also an idea that also Alex was mentioning this morning, the fact of bringing also the Doherty technology into the lower powers, okay? When the network's becoming more dense, it's also important to optimize the energy consumption in those lower powers as well. You have there an example of a compact 400 watts, 200 watts could be the same case, okay? So into the middle point of this slide, probably when we think about designing a new transmitter, what the most important element is a good selection of the latest and more advanced transistors, okay? And the design of all the Doherty circuitry around that transistor, okay? That is what is going to be the core of bringing the highest efficiency out of the unit. And there, if we are comparing older generation devices, we we could be talking about mid-20s%, probably not even low 30s if we talk about older devices. And now we can be talking about 50% average, or even reaching in certain particular cases of MERs, channels, and so on, up to 53, okay? And that brings significant benefits on it, okay? So there you have an example, okay, of a 2.4 kilowatt transmitter. There on the first row, you see, let's say, simulating a case of a 25% efficiency transmitter, and on the green line at 50%, not going into the best case of 53, let's say like that. And there you can see the number of kilowatts per hour that you are saving in a year, and also the amount of savings in, let's say, euros, if you really use a typical cost of electricity, okay? So clearly, this is one of the most important elements in order to optimize the energy consumption in a network. So transistor is one important element. I would say the second one is the selection of a high-performance power supply, okay? And a remark on that as well. I think that in general, all manufacturers are using same type of power supplies. Let's say this is nothing new to anyone, but it's important to use a model that in the end really keeps a very high performance if the power supply is not operating up to the maximum load, okay? So in the end, when you are operating a transmitter not up to the maximum power you can reach out of the device, the efficiency of the device is not damaged significantly, okay? That's an important factor there. And designing a high efficiency transmitter is trying to optimize how much efficiency you can get out of the transistor and the circuitry around it, and then try to lose as less as you can in the other elements. It's a game like that, okay? So here, the important thing is to try to minimize the losses and trying to avoid having any unnecessary over-dimensioning element inside of the box. So try to control the energy consumption on the signal processing board, on the control boards, on the pre-driver, on the driver, and probably especially there on the combining elements of the different palettes internally on the transmitter, and also between the different amplifiers when you are building a higher power transmitter. So taking care of all those smaller details is what it brings 1-2 points of more efficiency into a design, okay? Then this is a concept that Alex this morning was mentioning. I will mention it again, but I will not go too much in depth on that, because I think that Phil will give an in-depth speech on that from the Arqiva studies. But we all know that MER and efficiency are two parameters that are linked together. The higher you want the one, the other will be a little bit damaged, okay? So in the same way as, for example, on the TV transmitters, we have been always getting quite a standard request in terms of what MER the network operators are demanding. For DAB, there is, as Alex was mentioning this morning, quite a range, okay? People are demanding 30 dBs, others 32, other countries are operating in 26, and others are even thinking about, and they have already implemented, going down from that one. So it's a choice that each customer network operator would like to define how they want to do the network. So what we have come up with, or at least how we can contribute to this, is to try to bring an algorithm internally on the transmitter that helps that optimization to be done in a very easy way, okay? So the idea here, at least the way how we do it, is in our, let's say, web interface. We allow somehow the network operator to state what is the minimum MER they want to play with, okay? No matter what is the existing MER that the transmitter is providing, you can configure, let's say, for me it's enough with 26 dBs of MER. I just type there the 26 dBs of MER I want, and then internally, the device is already configuring voltages in power supplies and different elements there in order to achieve, at least to not go below that MER, but in that case, you are already optimizing the energy efficiency on the device. And this should go together with having a very good performance adaptive precorrection, because if you already do that, and you are optimizing already the maximum MER out of the transmitter, you don't need to penalize somehow the efficiency in order to increase a little bit the MER. Okay, so both things are contributing to also the fact of having a better efficiency there. So here is an example. Yeah, so for example, let's put this example. It's a 2.4 kilowatt transmitter in channel 7A, and we are, let's say, taking it out from the factory with an MER of 32 dBs and providing a 50% efficiency on that particular channel. And this transmitter, let's go, it goes to a German customer where maybe the requirement there is 26 dBs of MER. So they just type this 26 dBs of MER in their target objective, and you see there that they will be increasing the efficiency in around 3 points. Okay, so 3 points of efficiency in a 2.4 kilowatt transmitter brings that amount of savings in energy consumption and also in the cost of the operation of the network. If you multiply this by a certain number of transmitters, that really implies a big benefit for the network. Okay. Other ways how we, the transmitter manufacturers, can really make the network more efficient is if we bring into the transmitter some functionalities that are somehow initially meant to be in external boxes, okay? So in a typical transmitting site where you have like a standalone satellite receiver or whatever way to bring the signal into the site, okay? But let's think about a satellite receiver, a GPS receiver, a monitoring unit, and then you have the transmitting device. If you really bring some of those functionalities embedded into the transmitter, somehow you are optimizing the number of elements into the site, of course, the cost of the site, but also the energy consumption at the site, because those elements are consuming quite, not a big number of watts, but certain amount, okay? So for example, here, as we were saying before, we also count with our standalone satellite receivers, with redundant satellite receivers, redundant power supplies, standalone GNSS receivers with multiple constellations, multiple bands, and dual power supplies, and so on. So maybe that kind of architecture on the left could be quite interesting for a, let's say, higher power transmitting site. But maybe when you go into a lower power site and you want to optimize energy consumption, costs, and so on, some of those functionalities are interesting to be brought into the proper lower power transmitter device. So you have there the built-in satellite receiver, the GNSS receiver, and so on. Okay, so in the end, this is somehow another way of improving the efficiency on the transmitting side. And from the monitoring point of view, something similar, okay? You can have an external device to monitor the quality of the transmitter, but something that we have come up with, and others do something similar in different ways, but this is the way how we do it. Internally on the web interface of the device, you can really get a view in a historical way, in an histogram that you can export into many, many different formats, about the progress and evolution of the different, both internal performance parameters like MER, shoulders, efficiency, and so on, but also internal elements like voltages, currents, temperatures, and so on. Okay, so this is a way somehow to get from the transmitter device itself quite a lot of useful information about the status of that particular site, okay, or that particular transmitting element. So you could avoid somehow in certain particular sites to have another element to really do the monitoring of it, okay? So this kind of solution can help you from the point of view of troubleshooting whenever a problem could happen, avoiding less or helping to have less needs of visits to the sites, also some energy consumption there and environmental benefits there. And also could help somehow to try to do some proactive health check. So I just put you an example. Let's say a network operator wants to run a network and they put an MER threshold there of 28 dBs, okay? And you're operating a network there and the transmitter is providing 30 dBs of MER. At some point you have been getting these 30 dBs of MER for the last 6 months. But suddenly the MER starts to drop a little bit, okay? 29.5, 29.2, 28.7. At that point, there is no alarm, no trap in your NMS system. But if at the same time you start to see your graph of the MER dropping down, temperature of your whatever amplifier going up, the currents of the transistors starting to be a little bit unbalanced, it's already giving you an indication that potentially something is going to happen on that transistor or at that particular transmitter. So that could also is a way of helping somehow the prevention of future problems, and in the end somehow contributing to the energy saving if you need to go less times to the site. Okay, these are just basic numbers. So I mean, how much you could save with typical electrical consumption items on those devices. What is not such a big number as before we were seeing with the MER versus the efficiency, but everything contributes. Okay. And just the last few ideas, something that the transmitter manufacturers can also contribute with is bringing some, let's say, innovative solutions in a way of extending the coverage in a more efficient way, okay? So it's perfectly possible to do a full coverage just based on transmitters. It's logical, a way to do it like that. But in the end, the latest technology on the echo cancellation for SFNs is also allowing the possibility to install SFN on-channel repeaters in DAB+. Okay, and there are several examples of some members of the WorldDAB forum that have been already implementing sites on this kind of technology. Okay, so in the end, somehow you have a network where some of the sites you could avoid having this satellite receiver at the site, GPS receiver at the site. You are somehow optimizing the cost and also the energy consumption on the site. Yeah. And this is basically possible because nowadays the echo cancellers that are available, at least in our case, allow you to play with gain margins of 30 dBs, meaning that you can cancel feedback echoes that are 30 dBs higher than your existing coming signal. You can cancel multipath echoes, Doppler effect echoes with a low MER degradation. Okay, so you see there down on the right-hand side that there have been already successful installations of gap fillers in DAB+, in SFN, even operating in 100 and even 400 watts, okay? In specific sites where maybe the input signal is quite high, but that's a realistic situation that happens already on the field, okay? And just the final ideas, okay? So Alex was mentioning before the idea of bringing several channels in the same transmitter. This is a way of optimizing also the cost of energy per transmitter or per multiplex there. You could also have different architectures where you can have multiple channels in the same chassis where you are optimizing the cost and the energy consumption of each channel, as you see in the picture there. Bringing the endohertz technology into the lower powers is also an important element. And also that's something that helps at least from the environmental aspect in terms of less travel to the sites, is trying to automate as much as you can the manufacturing of a transmitter. We all know that when you are having quite a lot of manual processes in the manufacturing of a transmitter, the rate of potential failures goes up. Okay, so doing, let's say, optical inspections, X-ray inspections, having a fully automated kind of manufacturing plant really helps on the reliability, and the reliability that you could add also with redundant systems, with making the solutions more compact, less lighter in order for the transportation to become more efficient and a much user-friendly interface, makes all the process of the maintenance and the amount of trips you need to a site lower, and that also brings some energy benefits into the network operator. Okay, so as conclusions, okay, energy efficiency is clearly a hot topic today, and it will continue being for the next years due to main three reasons: the cost optimization in the operation of the network, because companies have policies that really force the energy to be optimized, and also the environmental aspect. So we Gates and other manufacturers, let's say that we have to understand our role here as a key contributor for the efficiency on the networks, and this is more or less a list of the ideas we just shared. using the Doherty technology with the latest transistors can bring efficiencies up to the level of 50–53%. Integrating more functionalities into the transmitter will also contribute to the energy usage. Making easy for the network operator to optimize the MER versus the efficiency brings also energy efficiency improvements. And latest echo canceller technology brings also the possibility to implement DAB gap filler systems in the networks, and making systems more reliable and more compact also bring some energy savings and environmental benefits. So I think that we, as transmitter manufacturers, can all contribute to the promotion of DAB Plus worldwide, but I think that our main contribution is to try to bring these kind of innovative solutions so the network operators can propose better solutions for the broadcasters, for them to be highly motivated to move into the DAB Plus kind of platform. Okay, so in the end, probably in the questions and answers sessions, we can just answer any question you may have, but that's more or less the ideas that I think that as transmitter manufacturers we can bring to optimize energy. Okay. Thank you.
Okay, Luis, thank you very much for this interesting and very comprehensive presentation on the efficiency of transmitters. So now let me introduce Phil Casby, who will give us a presentation on how BBC and Arqiva are reducing the environmental impact of a national DAB transmitter network in the UK. Phil, the stage is yours. The clicker is here.
Okay, thank you very much. Okay, so so DAB in the UK is the most popular way that consumers are consuming their radio services, but increasingly broadcasters are required to develop and then fulfill new sustainability targets. Now, one way in which broadcasters can achieve a reduction in energy on their networks is to re-engineer, perhaps for some of the legacy equipment might be natively a little bit less efficient, but sometimes re-engineering can be a bit cost prohibitive. So this joint project between Arqiva and the BBC, this is a attempt and is a project which we basically looked at our existing norms, and we've challenged some of the ways in which we've done things in the past to see if we could actually reduce the energy in our BBC DAB network in the UK without impact on the consumer. So just to set the scene then, so the BBC have published their sustainability targets, and they have a requirement to reduce the energy consumption on their terrestrial platform. That's not just DAB, that's all of their terrestrial platforms, by 28% by 2030. So for the DAB component of that, the BBC DAB network consumes approximately 10 gigawatt hours per year, which is roughly about 13% of the total BBC energy consumption across all their terrestrial platforms. So what does 10 gigawatt hours per year sort of look and feel like? Let's put that into some sort of parameter that we can all sort of understand a bit more. So 10 gigawatt hours per year is roundabout continuously powering 4,000 average size UK homes. So it's a considerable amount of energy, and the objective really is to try and reduce that a bit. Going into that network, there's over 400 transmitters, and they provide coverage to 97% of UK homes. But that network has been built out over the past 30 years. Some of the transmitters are of a design where they're not very configurable, and their native efficiency is anywhere between 15% and 25%, up to the much more modern design of transmitters, which we've heard about already, the Doherty design. We have a large number of those as well, and their efficiencies are much better, anywhere from 30 or 35% up to 50% or so. So of our network, about 150 of those transmitters are the more modern types, the Doherty types,
And it's those transmitters that we're targeting in this energy reduction campaign because they're more configurable. And of that network, of that 150 transmitters, they consume approximately 2.4 gigawatt hours per year of the energy from that 10 gigawatt hours of the total consumption of the whole network. So DAB uses wideband OFDM. We've got 1536 carriers using DQPSK modulation, and we modulate each carrier 2 bits per carrier per symbol period, making it fantastically robust, and it's perfect for things like mobile reception. On the left-hand side of the diagram here is a time domain composite representation of the DAB signal. When those 1536 carriers don't all add up in phase, we can call that the mean amplitude of the signal. But when they do all add up in phase, we get these higher level of peaks. So in older amplifier design, what we used to have is power supplies that were capable of coping with these high peaks. Now that's great for maintaining a really high quality RF signal, but it's sometimes not so great when you want to improve the efficiency of the amplifier. So what can we do with this? Well, we could, and we do, choose to clip those peaks. So statistically, we have all of these carriers adding up in phase every so often, and we can clip them. But by clipping those peaks, we need to be really careful, because clipping those peaks creates in-band and out-of-band intermodulation products. Out-of-band intermodulation products, we need to be really careful, because we can, if we do this too aggressively, we can exceed our filter requirements, and we can get in trouble with a regulator, and we can impact adjacent users. And then the in-band intermodulation products, if we clip too aggressively, we lower a parameter called modulation error ratio. We talked about it a lot all day, but basically by doing that clipping, increasing those in-band intermodulation products, we drive down the MER, and we need to be careful about that for the following reasons. So MER on the receiver then. So MER on the receiver is really made up of 3 main components. It's receiver noise, which is a function of receiver design plus the native technology. It's about channel impairments, which I'll come on to in just a bit. And it's about the transmitter signal quality, this MER. And on the right-hand side, you can see a graph, which is the relationship between the transmitter MER configuration and impact on coverage, which is effectively the same as a power reduction of the transmitter. So if you go along the x-axis, what you can see to the right-hand side is that at 30 dB MER, which is a quite typical legacy MER configuration for many broadcasters and network operators, you can see that the impact by having a transmitter with 30 dB MER is absolutely minimal on the receiver. However, as we've been discussing also this morning, with MERs that are high, often that lowers the efficiency of the transmitter. If you go along the x-axis to the left, we're reducing the MER, and the efficiency improves. But ultimately, especially when you get to the far left-hand side of the graph, if you degrade the MER too much, it can dominate the receiver. This is obviously a really bad place to be going, and no one's proposing that you drive the transmitter with MERs with very, very low numbers. Now, the shape of this curve is described here, but the most important thing to take from this is that this is non-linear. So what I mean by that is that there's an area of interest. So historically, Arqiva and the BBC, we've configured and had a target of 25 dB MER. But what you can see is the shape of that curve when you go from 25 to 20 dB MER, the effective power reduction of the transmitter or impact on coverage is very, very small. Is there a, yes, there we go. So if you can just about see the little red dot on the graph there, we expect to have an effective power reduction of the transmitter or impact on coverage of around about 0.1 of a dB, which we think is probably unmeasurable. And we don't think there will be an impact on the consumer by doing that change. At least that was our initial thought in this project. So of course, if that is proven to be the case, what we want to do in sympathy with that is change the configuration of the power supply. So if we can afford a relaxation of the MER and we can change the configuration of the power supply, we've then got a transmitter which is more efficient, and hopefully we're not going to impact any of the consumers. So how do we test this then? So we started off with some bench testing. And what we did is that we took a baseband ETI file from the WorldDAB ETI file library. And we pushed that through a software modulator to create some IQ samples. And then we pushed those IQ samples through an amplitude clipper. And depending upon how that amplitude clipper was configured, we ended up with a range of RF files with different MER values. So we created a number of RF files ranging from 30 dB down in 5 dB steps down to 5 dB MER. Once we had those RF files, we could then put those onto the signal generator. In this case, it's a Rohde-Schwarz broadcast test center. And we could play those RF files one at a time into a reference DAB receiver. And in this case, for us, it's a Rohde-Schwarz ETL. So we chose a threshold of errors, and we put the first 30 dB MER RF file onto the signal generator, and then we increased, on the right-hand side, you can see there's a box that's called AWGN. That's a wideband noise source. So with that at a low level, and the 30 dB MER RF file being played into the receiver, we slowly increased that wideband noise source until we got to 5% errors. That was our threshold. And we wrote down the number on that AWGN, that noise source, on the signal generator. We then replaced the 30 dB MER file with a 25 dB MER file and repeated the same test. And it's the difference, the difference between the AWGN setting, which we needed to record. And we did that for each file, each RF file, and effectively that allowed us to reconstitute that curve that you've seen on the previous slide. However, the story doesn't quite finish there, because in the real world, between the receiver and the transmission site, you've got a combination of paths, RF paths. In some locations in the old transmitter coverage, you'll have a Gaussian channel, and that basically means that you've got a good RF path between the transmit antenna and the receive antenna, but you'll also have a fading channel, and that's because there's lots of reflections, either locally or long distance. And the big difference between these two conditions, which we need to plan for in our networks, is we need a higher S upon N between the Gaussian channel and the fading channel. So the final box on this signal generator, is that working? Yes, just about to see it, is this fading channel simulator. So we repeated all of those tests I've just described, firstly for a Gaussian channel to see if our results lay on our theoretical curve that we've just described, and then we repeated them again for the fading channel, where you need a higher S upon N to get to the same reference BER threshold. So the results then. In fact, before I get to the results, we've now got two curves on this graph, and the reason for that is going back to this difference in S upon N between a Gaussian and a fading channel. One of the components in our theory, if you like, is that we have S upon N as part of the requirement for this impact of MER on coverage. And because we have a higher S upon N for our fading channel, you can see that the dotted line here is the fading channel curve, and it curves earlier. The other curve, the solid line, is for our Gaussian tests. But this was the first breakthrough for the project. Rather, as previously thought in spectrum planning considerations historically, where you would undertake this test, rather than in a fading channel, the results effectively landing on the fading channel curve, they all converged on the Gaussian curve. And this is because the MER noise, as a reduction of the transmitter, MER, is explicitly linked to the carrier of the transmitter, and it is Gaussian in its structure. So that is why it fits onto the Gaussian curve and does not sit on the fading channel curve. So why does that matter? So this gives us even more confidence that we can actually start to look at 25 to 20 dB MER as a way to relax the MER of the transmitter, modify the power supply, and save some worthwhile energy. So now we're ready to go and do some tests in a live network. So we had enough confidence from our bench test to actually go and do this for real. So we chose a site called Clun, which is in the live BBC network. It's a 600 watt ERP site. It's rural, but we chose it because of the coverage. So to the east of the site, we have a significant amount of SFN overlap. So we have contribution from other sites coming into the Clun transmitter area. We've obviously got dominant Clun only or dominant transmitter conditions only. But to the west, we've also got edge of coverage, which is actually quite tricky to find in the BBC network because it's such a dense network these days. But it was a perfect site for us because we've got all of the three main characteristics that you would find in the live network. So the transmitter was configured to be either at 25 dB MER, 20 dB MER, or even 15 dB MER. We're not proposing that as a configuration, but we want to do that for experimental reasons. With the transmitter at each of those MER configurations, we also measured the mask, the output of the mask and the output of the filter to make sure that we were still compliant. And we used a mobile measurement approach where we actually did a comparative approach where we did drive tests with the transmitter at one configuration, then the next, then the next. We used the Radioscape observer for that, so we could tag all the measurements, the GPS, and we could measure signal strength and BER and so forth. So for the measurements between 25 dB MER and 15 dB MER, we actually couldn't see any difference between SFN overlap conditions or dominant single site conditions. It was really hard to see any difference. It was within inside measurement error. However, at the edge of coverage, there was a difference between 25 dB MER and 15 dB MER. We were quite glad because we were thinking, crikey, something's got to be wrong if you push it too hard and you can't see any difference. So there definitely was. But what you can see on the screen, because of that non-linear shape of the curve we talked about already, what we've got is 25 dB MER versus 20 dB MER. Now each of the little pixels, these are 50-meter pixels, and we've categorized them so that the green pixels are between 0 and 5% errors, which we call in coverage or in service. The yellow or amber pixels, they're between 5 and 10% errors. That's edge of coverage. And then the red pixels is not in coverage. But what you can see is that the difference between the 25 dB MER drive test at the edge of coverage and the 20 is very, very similar. There is a little bit of a difference where on the left-hand side where you see edge of coverage, maybe a pixel or two difference, but where the actual receiver failed is within maybe 50 meters or less when we did this drive test. So this slide kind of says the same thing. It's the same stretch of same stretch of road where we did the drive test. You can see on the x-axis, it's the distance from the start of the drive test for this edge of coverage test, going from good coverage, going to the left on the x-axis to through edge of coverage to out of coverage from the transmitter. But the point is, if you look at the average pre-Viterbi BER, whether it be at 25 dB MER configuration, which is the orange line on this graph, or the blue, which is the 20 dB MER for the transmitter, the performance for the BER is quite similar between both of the drive tests. So now I'm going to show you two videos. The first is the same stretch of road again, firstly at 25 dB MER. The second video is at 20 dB MER. This is a live test on a live network. So the first thing that you'll see is that the audio is different between the two clips because obviously they've been done at slightly different times. The other thing is, before complete failure, you'll hear a few interruptions to the audio, and that's because we're already inside those orange pixels, so we're already between 5 and 10% failure. So I'll play them and let's see if we think the failure location is around about the same place. Okay, that's 25 and 20. Okay, so I hope that you'll agree with me that the failure location was around about the same location. It was the house to the left-hand side of the video. You saw the entrance to the driveway. It's around about that location for both of those videos. So in our conclusions then, so we've done extensive lab and field measurements. We believe that we can carefully adjust the MER down from 25 dB MER down to about 20 with negligible impact on coverage. When you combine that reduction MER with power supply optimization, we think there's worthwhile energy savings to be had. For us, what we found is that the energy savings before and then the after was between 4 to 16%. So what do we mean by that briefly? The 4% is if you take a transmitter from a manufacturer at rated power. So if it's a 300 watt transmitter and you operate it in a network at 300 watts at 25 dB MER, the energy savings is 0. If you modify the MER at rated power and then re-optimize the power supply, we find about 4% saving. And the range then to the 16% is when we've got the same process, but we're taking the same 300 watt example transmitter, but now that's down to -2 dB with regard to the rated power of the transmitter. So we're finding much greater savings for transmitters which are underrun when compared to the manufacturer's rated power, which is quite common. So we don't always run the transmitters at their rated power. Often we have to configure them to be lower than their rated power because of site-specific things and license requirements. So when we add all of those things up, we end up with about 0.3 gigawatt hours per year savings. We're rolling this out now into the network. And it started in the autumn of 2024, and we're concluding that work this year in 2025. And so far, we've found an average improvement of around about 12% in our network, which is definitely very nice to have and goes back to our sustainability targets, which is great. And the final point really is that we're not just doing this by going to the site all the time. We're actually working with our transmitter manufacturers to actually, as best we can, try and automate this so that we don't have to keep going back to the site and using more carbon through driving cars and so on and so forth. So we are automating as much as we can, but not only do we then cut down on the trips in the car, if you automate it, the other thing you can do is that you can absolutely maximize every single installation. So that means that we absolutely hit the required MER requirements, and we make sure we don't miss our shoulders, which is plus or minus 970 kilohertz. We don't exceed our shoulder performance, and therefore we don't break our commitments to UK Ofcom. Okay, that is me. Thank you very much indeed.
So thank you very much, Phil. I have been told that the audio from the video was very low. So online they had problems hearing it. So maybe if it's okay, we will try to replay the videos at the end of today's session for those online, if that's okay. Okay, thank you very much. So thank you, Phil. It was a really brilliant presentation, very interesting. So that brings us to the end of the second session and to lunch. So we will see here again at 12:40. Okay, hello everybody. It's 12:40 and we are back for the third session of our seminar. And let me introduce Carlo Perotta from Aldena, who will give us a presentation on antennas and how to make DAB transmissions more efficient. With a very interesting title, he will tell you more. Carlo, the floor is yours.
black session is coming. Thank you, thank you, Hans, for the introduction, and good afternoon, everyone. Welcome back to the last session of the seminar. Thank you again for joining us today and attending online. So there is no doubt that broadcaster network operator are facing a significant challenge in terms of energy cost and energy consumption. There is a constant pressure to reduce cost and maintain high quality services. And often we have a situation where the budget is limited, but we need to increase the quality of the services. So now you can understand a little bit the reason of the title of my presentation. The antenna design can lead to improve the performance and the efficiency of the network and the energy cost. And antenna design is one of the key to manage in the right way the energy consumption. So let me spend first few words about my company, Aldena. We are an antenna manufacturer, one of the historical European antenna manufacturer. We design, produce, and deliver tailor-made antenna system for radio television application, for analog or digital services, customize antenna for mission-critical application, and special solution for monitoring and measuring purpose. Together with the antenna, we provide added value engineering services like network planning, antenna design, commissioning, training activities. For example, we have developed the largest antenna test plan area in Europe for testing broadcasting antenna. And together with the antenna, thanks to our branch company, Delta Mechanica, we can provide an extensive range or additional portfolio composed by coaxial component like dummy load, switch, RF switch, transmission line, rigid line, and accessories. In addition, we provide an innovative line of filters, star point combiner, and dual bridge combiner to achieve low insertion loss, high selectivity, and temperature stabilization. Not only metal, many antennas and network have been designed worldwide by using our software. Electromagnetic Lab is an all-in-one solution for different activities, different applications like antenna design, coverage or interference calculation, and RF exposure compliant calculation. Today is used by different radio and television operators and different telecommunication authority and regulator are using it. Here, for example, there is an example of coverage calculation that we performed for the last DAB trial that we delivered the SAM antenna for last year. Let's move to the main topic of my presentation. Antenna design is part of the network planning process. As you can see, is not an easy task because our network can be local, regional, or national, but we have to reach different targets altogether. So for sure, particular attention to the transmission cost and saving energy, but in the same way, we have to guarantee the best coverage and the best quality on the target area. Speaking about DAB, target area can be a city, a particular city can be a specific highway. So we have different target, indoor reception, outdoor reception. And in a parallel wave, we have to taking care about the frequency planning. So we have to coordinate the national and international frequency, and we have to fulfill the obligation from the network planning that normally comes from from the authorities. And of course, in case of SFN, we have to minimize the interference. And in case where the tower is located close to the city, we have to control and manage the RF exposure compliance for the human body protection. If we move to the general point of view to the antenna, and we speak about efficiency of an antenna, the antenna gain is our efficiency. So the gain is our directivity. So the capability to concentrate our energy in a specific direction. And ERP, the effective radiative power, is the magic number that we have to manage, the combination between the power generated by the transmitter and the antenna gain. So this is our normal challenge that we have to manage. So define the best trade-off between the antenna gain, the transmitting power, and later on we will discover that other items influence our energy consumption, in particular filters, transmission line, combiners, and all the other equipment beside the transmitter. So how is possible create and customize pattern? For sure, we can select from the market different antenna type. You see dipole, traditional dipole solution, or panel solution, or high gain log periodic antenna. We can select the single items and start to create and customize our horizontal and elevation pattern to achieve a specific ERP for various towers, because for triangular tower, square tower, and so on. How is it possible? We can select, again, different type of radiator, different antenna type. We can manage different power distribution between each radiators. And for sure, we can introduce phase modification or azimuth modification and the relative distance, change the relative distance between the radiators to tailor-made our pattern and our solution. Some real-world case study. Here, for example, a specific antenna that we developed to obtain the best coverage in some location that was provided by the final customer. You see different distance and different azimuth location between each tower positioning, city positioning. And of course, here we are in an ideal situation because we have a lot of free space in the new tower, and we can develop an amazing antenna with a total gain about 21 dB. So it's incredible gain. But this means that we can save a lot of power, reducing the transmitting power cost. Otherwise, other example, in this case, we use very high gain log periodic antenna to create spatial reduction in specific direction. In the example, we have more than 30 dB reduction in some area. The target is minimizing the interference. In case of SFN, another magic number is 74, is the maximum distance between the DAB transmitter. Or we can fulfill the obligation from the network planning, because, for example, in Italy, the authority give us some specific test point that we have to guarantee the minimal signal strength in Italy and in our neighbored countries. Another case study, this is an omnidirectional array configuration, but the blue line is the specific ERP limitation provided by the authority. So we reduce about 3 dB the irradiation in the specific direction, so to fulfill the obligation from the authority. Or another example, in that case, the customer requests us a omnidirectional antenna, but the tower side was very big, about 7 meters, so it's impossible to use the normal array composed by 4 directions. So we develop a special array composed by different antenna to obtain a real omnidirectional antenna. So in any case, when we start to increase the number of the antenna, general point of view, we increase the total gain of the antenna system. So what we have to do is try to use all the free space that we have available on the tower to increase the gain. And keep in mind the general rules about the antenna design. So when we double the number of the antenna, we increase about 3 dB the total gain. This means that we can achieve the same ERP by using half power. And this is crucial in the energy cost and energy audit that we have to manage. A simple but a relevant example, how we can achieve 10 kilowatt ERP. We can approach in the simple way, just using a couple of dipoles. This is typical in the local coverage for DAB application. And total gain is about 5 dB. The input power can be about 3 kilowatt. Otherwise, we can obtain the same level of coverage, the same ERP, just using 4 dipoles. So we increase about 3 dB the total gain. We spend a little bit more space in the tower, but at the end, we can use half power. This is a general overview about the antenna design rules. But just let's go a little bit more in details. So general point of view, we have to consider everything in our transmission station design. Of course, Luis and Alexander, I don't want to speak about efficiency of transmitter, power supply, transistor, or high cooling system definition, but keep in mind that it's relevant any items that we add beside the transmitter, because it can be a relevant influence in terms of insertion loss that we included. So when we select filters, combiner, feeder cable, connection system, the rigid line, this is very important, taking care about this selection, because all this selection influence the total power that go to the antennas. You see the general formula. So the total power that we have at the input of the antenna is reduced dramatically when we have a wrong selection of filters and combiner and transmission line, for example. Let's explore together some general numbers. You can see, of course, different cable type, foam cable or air cable, for taking care different power level. But have a look, the big difference in terms of attenuation, starting from half-inch cable up to 158 foam cable. This is normally the foam cable are used typically for DAB application because we don't need too much power. We are digital. You see all the other presentation before me speaking about the advantage of digital signal. And the same consideration we can introduce by choosing different filters. Apparently, the dimension of the filter introduce low insertion loss is something 0.1, 0.2 difference. But at the end, what we obtain is a dramatically reduction of the efficiency of our system. So taking care about which filter you are using, which transmission line you select. Let's move to some example. I try to introduce you some an exercise, some calculation, some example to analyze the transmission cost and the insertion loss that we can introduce if we make different selection. In the case study 1, we have a transmitter about 2 kilowatt, and we introduce a conservative approach. We don't have too much budget, so we use a 7/8 rigid line, a simple filter, and 7/8 foam cable. What we obtain is 2.3 dB insertion loss attenuation. Otherwise, if we move to 158 rigid line, foam cable, and we introduce a new filter with a bigger filters with different cavities, we can save around 1 dB. So total loss will be 1.5. What does it mean? That at the end, we reduce dramatically the power that comes to the antenna. And of course, this influences the total ERP that we will use for covering our target area. The difference is, in the case 1, we wasted 240 watt. Now, let's try to add the antennas, because this is our main activity. So in the first case, again, we don't have too much budget, so we use just 2 dipoles. And in the second case, we use 4 dipoles. So we double the number of the antenna. At the end, we can gain around 5,200 watts. So we have a big difference in terms of total ERP. So if we image that 8.9 ERP, it will be our target for covering the specific area. What's happened in the case 1 versus the case 2? So we want to obtain the same ERP, 8.9. At the end, we have to change the transmitting power. So we have to increase the transmitting power of, in the case 1. So at the end, if we add some typical value and the typical cost analysis using 40% of efficiency and 0.25 euro for kilowatt per hours, we can obtain a significant difference in terms of energy saving consumption in the case 1 and in the case 2. If we add the cost of the material, so I'm speaking not about the transmitter, but about antennas, feeder, and filters that we use in the case study 1 and case study 2, you can see that is only an apparent cost saving about the capex, because just increase the investment about 4,600 euro, we can achieve a very big amount for years in terms of cost saving and energy consumption. so we can maximize our operational efficiency. We can reduce cost, but not the performance. At the end, keep in mind that, of course, antenna design is a crucial point of our analysis. We need to optimize our antennas. We need to use the proper antenna for our specific network planning process, and of course, obtain an energy consumption reduction. Thank you. Thank you for your attention. And see you in the last section. Thank you.
Okay, thank you, Carlo. A very interesting presentation. And this takes us to the last presentation of this session, which is from Justice Appia, who is not here. He has sent us his presentation as a video, and let's see if it will go online.
Hi, everyone.
Okay.
Thank you for joining me today virtually. My name is Justice Appia, and I'm a telecommunications engineer at the National Communications Authority, Ghana. I was really looking forward to being with you all in person, but due to unforeseen circumstances, I will be presenting to you online today. The topic of my presentation is running DAB off the grid. This is an exciting and highly relevant subject, especially as we explore sustainable and innovative solutions for modern broadcasting. I hope this presentation will not only inform, but to spark meaningful discussions about the future of broadcasting and renewable energy. Please feel free to ask questions and share your thoughts. At the end of this presentation, I would like to hear from you about your own perspectives about this important and innovative topic. Without further ado, let's dive into the presentation. Throughout this period, I'll walk you through the key aspects of this topic, including the DAB trial in Ghana, sources of renewable energy, Ghana's DAB transmission infrastructure, and of course, the big question, why run DAB plus off-grid? We also talk about the benefits of running DAB plus off-grid, how it works, its environmental impact, and the challenges and solutions relating to this innovative solution. And the last slide will be about the conclusion of this presentation. In August 2023, Ghana launched its DAB trial in Accra and Kumasi, in the Greater Accra region and Ashanti region, respectively. This trial was launched in Accra and Kumasi because these are the two major cities in Ghana that is most populated in terms of economy, in terms of population. They are the two biggest cities in Ghana. So the government of Ghana decided to have this launch in these two cities to know how this technology can be implemented and adapted by Ghanaians. For the purpose of this presentation, I would like to share with you some of the sources of renewable energy. And these sources, I believe, are in every country. So depending on your country and depending on what is available, this renewable energy can be harnessed and then converted into electrical energy. So the likes of wind, hydropower, and then solar. Wind, as we all know, we generate energy from the wind using the wind turbines, and hydropower from the flowing water or falling water, typically using dams or runoff systems. And then solar, which is the common one. We all know harnessing energy from the sunlight using the solar panels or solar thermal systems. Let's all watch this video about Ghana's DAB transmission infrastructure. And after this video, we will continue the presentation.
In the heart of Ghana, where innovation meets creativity, stands a beacon of technological advancement. Welcome to the Ajangote Digital Terrestrial Television DTT and Digital Audio Broadcasting DAB Plus primary transmission site serving the capital city of Ghana and its environs. This remarkable site is powered by an impressive 160 kilowatts of clean, sustainable solar energy, ensuring uninterrupted service 24 hours a day, 7 days a week. The Ajangote site is the lifeline of broadcasting in Accra, serving the majority of Accra and its outskirts. This is a transmission site for both digital terrestrial television DTT and digital audio broadcasting DAB Plus in Accra. These transmission sites play a vital role in bringing you over 45 DTT channels and 18 DAB channels in Accra and Kumasi, delivering news, education, entertainment, and sports right to your screens and speakers. But what sets these sites apart isn't just its cutting-edge technology, it's a symbol of progress, innovation, and commitment to the people of Ghana. Say goodbye to interference noise on your radio. With the newly launched DAB Plus pilot project, radio stations can now reach more cities beyond their immediate locations, providing you with a broader range of program content featuring 18 channels. This pilot positions Ghana as the first country in West Africa to deploy DAB Plus. Accra and Kumasi DTT and DAB transmission sites where the future of broadcasting shines brighter for you and for Ghana.
Welcome back. It is evident that Ghana's DAB and DTT sites are powered by solar from the video we just watched. Yeah, and these are the few parameters that we have on our solar system. We have a panel capacity per site. If I say per site, I mean Accra and Kumasi. We have 150 kilowatt peak panel capacity per site. The number of panels we use per site is 300 panels. And then the government of Ghana also used the 150 watt panels. That's the type of panel per site that the government used. For your information, this site was originally built for the DTT network, but for the purpose of this DAB, 40 kVA was added for the purpose of this DAB. Yeah, so the site also has a battery capacity of 880 kilowatt hour, and then averagely, the daily energy generated per site is around 750 kilowatt hour. These are some of the pictures from the video that we just watched about the DTT and then the DAB sites in Accra, which is powered by solar. This presentation is all about running DAB off-grid. And of course, the big question, why should we abandon our traditional way of providing power to our broadcasting transmission sites by the grid system or the national grid system? Why should we do that? First and foremost, access to reliable electricity is critical when running DAB Plus system off-grid. Since off-grid systems operate independently of the national power grid, the use of renewable energy like the solar, the wind, ensures stable and continuous power supply and can greatly achieve reliable and uninterrupted broadcasting. Secondly, it reduces dependency on national grid. Running DAB Plus off-grid significantly reduces the dependency on the national grid by leveraging independent power sources and self-sustaining energy systems. This approach is particularly beneficial in remote areas during emergencies or for companies seeking greater energy independence. Lastly, running a DAB Plus system off-grid aligns closely with sustainable goals by reducing environmental impact, promoting renewable energy, and supporting long-term ecological and social benefits. Off-grid DAB Plus or off-grid DAB system contributes to sustainability by reducing carbon emissions, reduction in destruction of natural habitat and ecosystems. Running DAB Plus off-grid has so many benefits. First and foremost, it saves cost. Renewable energy sources like solar and wind have minimal ongoing fuel costs compared to grid electricity or diesel generators. Over time, the savings on energy bills can offset the initial investment of grid infrastructure. Avoiding grid connection fees is also one of the ways to save costs. Connecting to national grid can involve high upfront costs, especially in remote areas and other areas. Off-grid systems eliminate these expenses. It also reduces operational cost. Running off-grid or DAB plus off-grid requires less maintenance compared to traditional grid connected systems, especially when using renewable energy. Secondly, emergency preparedness. This is also one of the key advantages of running DAB plus off-grid. Off-grid systems are more resilient during natural disasters, grid failures, or other emergencies that disrupt national power supplies. Transmission sites for emergency services, disaster response, or defense often need to operate independently of the grid. Thirdly, running DAB plus off-grid makes it scalable, i.e. easy to expand, easy to scale up or scale down based on energy needs, unlike our traditional grid connections, which may require significant upgrades. Also, renewable energy systems can be incrementally expanded as the company operations grow. For example, a broadcasting company, which might start with a small solar power site and expand it as and when the demand increases. Lastly, you have your own independence and you have your own reliable source of electricity. You have your freedom from grid constraints. You also enjoy the flexibility in site selection, i.e. companies can set up their broadcasting transmitter sites in optimal locations without being limited by grid availability. I don't know about your country, but in Ghana, not everywhere has the presence of the grid. So at least running a DAB off-grid in some areas would definitely help the country. So for example, a broadcasting company might set up an off-grid transmission site in a particular area for specific listeners. Let's quickly go through how this works. Okay, the technical side or the technical brain behind the whole implementation on the off-grid. So for example, FM stations, it can be 15, 18, 12, depending on the country's technical setup. For example, they send their feed through the audio processor or the encoder and then to the head end. The feed is then multiplexed into an ensemble. The ensemble travels all the way to the transmitter site. It can be by IP network or by satellite. Now, the transmitter site is where our concentration is. How is it powered? How does it get its energy to do its work? And that is why we are promoting this green energy. We are promoting this renewable energy for countries to buy into the idea to power these transmitter sites by renewable energy to enjoy the benefits that has been described in the previous slide. This seminar seeks to promote green broadcasting solutions to reduce or eliminate the impact of our conventional system of power generation on the environment. I will encourage all broadcasters to support this initiative to reduce our reliance on fossil fuels and grid power. We should utilize the abundant solar and wind resources that we have in our countries. We have a lot that we can utilize to to promote this green broadcasting solution. By promoting this or by practicing this, we are also aligning ourselves with global climate goals. And the goal is to achieve minimal or zero emissions to disturb the ecosystems. It is a fact that any new technology, any new evolution has its own challenges. And of course, every challenge has a solution. First and foremost, the first challenge in running a DAB+ off-grid or any broadcasting transmission site off-grid is a high initial cost. And this is a fact. Setting up this system requires a significant upfront investment. But the solution is to use a modular approach to scale the system gradually, spreading out the cost over time. Another challenge is technical expertise. Running a DAB+ off-grid requires specialized knowledge for installation, operation, and maintenance. If your country lacks this, the solution is to train staff or hire experts in renewable energy systems. You can also partner with reputable renewable energy companies for installation and maintenance support. Another challenge is the energy storage limitations. Off-grid systems may have limited power generation capacity, which can restrict the scale of operations. By the use of smart energy management systems, we can overcome this challenge to optimize the energy storage. Weather dependency is also a challenge. Solar and wind energy generation depends on weather conditions, which can be unpredictable. For instance, in Ghana, we have 2 weather seasons throughout the year. We have the wet season and then the dry season. Imagine using an off-grid system in the wet season or the rainy season. You can imagine what will happen. But its solution is to install oversized solar panels or wind turbines to generate excess energy during favorable conditions, which can be stored for later use. Next, regulatory and licensing issues. I work with the regulator. Sometimes operators face some sort of hurdles with us, but other regulatory bodies such as the environment regulatory bodies in our regions can sometimes bring out strict energy policies. We can work closely. Let's all of us work closely with the regulators, and let's ensure compliance with the regulators. I work with the regulator. If operators ensure compliance, we are happy to work with them. We are more than happy to be with them always and to help them for their business to grow and for whatever they are doing to succeed. Lastly, security and theft. This is also a major problem, especially in remote areas. In remote areas, transmission sites are vulnerable to theft or vandalism. And this challenge can also be overcome by installing security measures such as fencing, surveillance cameras, and alarms. Or we partner with the local communities to protect their infrastructure. In a nutshell, it is evident from this presentation that off-grid DAB+ is a sustainable, inclusive, and innovative solution. Of course, it bridges the digital divide and empowers communities. Imagine a village where there is no grid system, there is no light. If the system is installed, what will happen? They'll be able to at least have a feel of being part of the country because they have this solution and they'll be able to hear what is happening. Information dissemination will be faster and smoother. And lastly, Ghana also, the trial in Ghana also sets an example for Africa and the world, as we saw in the video. Thank you for this opportunity for me to share my ideas on running a DAB Plus upgrade. Questions are welcome, and I'm available online to answer all your questions. Thank you once again.
Let's come to our Q&A session. I have a significant list of questions already here for our panel and for our speakers. If you are online or if you're here in the room, if you have other questions, or raise your hand or send in the questions. We have a lot of time for Q&A, so we can ask them everything. They are available for everything. I will start with a little bit a general question, but it goes to Adriano, and then I will turn it also to the rest of the panel if they want to answer the question. You're not obliged to do it, but if you have something to add, it will be welcome. And that's for a country which is starting its DAB Plus journey. What one key piece of advice would you really give, having learned now from a lot of errors and problems and issues you have fixed over these years?
Good question, thank you, and I hope it will help. I think the first and the most important is to talk to each other. I said it before, it's really important to bring every actor, so every people that are participant in this journey, bring around the table. And this was the case in Switzerland, where the regulator, the public broadcaster, private broadcaster, the retail, the car industry, all these actors came together and created this roadmap in 2014, where we defined steps and goals for the next time. And this was a commitment from all the industry, where everyone could bring his personal organizational interest in this roadmap and journey. And so I think it was really this talk to each other, plan and discuss before, and then define this roadmap together. This is more on the organizational part, and I think this was really a success. The other one is the planning of the network. There we have, for example, on the EBU, the technical report 51, where you have different thinking and how to plan the network and measure the network, because every topography, every region is different, and so to have from begin a good planification of the network, and so you can have the maximal gain at the beginning and at the end fulfill the last little region that are needed.
Okay, but is there something you did wrong? And let's say, and which you suggest or you want people, newcomers to warn not to do? Is there, or maybe not? I mean, of course you can say, no, we did everything right.
I don't know what's wrong or we could improve. But I think this talking to each other was a success, where it perhaps we could be a little bit more strong was in some decision to be sure that this decision aren't remise en question, changed afterward. So have a better planification on this one. I think this could be something, but it's a real world. The situation changes, so the reality changes also. But at this level, I think that talk to each other is the most important, and have a common goal, and then that the regulator fix all these milestones and that this one are respected.
Yeah, thank you very much. I think this this has been a strength of the Swiss, really, in your process to switching off FM, really, your collaboration between all the actors. So congratulations. I would ask also Phil, because you have a long experience on DAB, and the UK is one of the most advanced countries, definitely, in the implementation adoption of DAB. So is there any advice you want to give us?
So I think there's two things with the benefit of, as you say, the UK having developed these networks over many years now. I think the first thing is don't forget resilience and redundancy. First off, maybe you think about the short-term gain, about putting equipment, not just at the transmission side, but also about distribution. You maybe think about having a network where you have more sites perhaps, and at each of the sites, maybe you just go for the minimum that you need to get the network on. But actually in the long term, sometimes having redundancy and the ability that when something goes wrong, you don't immediately then have a shutdown or you have to go and repair it or replace it. So resilience in a network is key, and thinking about the threats to the network in terms of network stability in the long term. So we had a great discussion yesterday about GNSS, and it's about trying to make sure the network is as secure and stable as you can in the long term, and sometimes putting that thought in at the start to try and get that design as robust, but obviously there's always cost pressures, but to try and get a robust design that is stable in the long term is a good thing. The other thing is, again, possibly easier said than done, is think about the type of network you need. So what I mean by that is it right to perhaps have a more dense network if you're looking for mobile reception in car? Maybe you have a slightly larger number of sites, maybe at lower power, to create a dense network to maybe make mobile reception better, or are you targeting a different type of application where you maybe have a smaller number of higher power sites? So it's those kind of things that if you put if you can, the thought in before you start building, sometimes it makes the network work better for you in the longer term.
May I add some question on this? I'm coming from Spain, okay? And Spain is now in a process where we have already more or less around 4 million cars already with DAB receiver already integrated. We have also the interest from the national public radio into coming into DAB. And when I have here the cases of the UK, Italy, and Switzerland, okay, as successful examples of how all the entities got really motivated and interested in coming into this technology, when you say that everybody sits together and they bring what they really need, how did you start motivating all the players, in particular like the private radios, where at the beginning probably maybe they see in DAB more a threat than a benefit, okay? So how did you, in your particular countries, manage to move forward from that existing position? At least in the UK, Switzerland, or even yourself in Italy, if you know it.
I will turn the question first to Adriano because they did the best job.
Yeah, it's a good question. It's funny because the need of new frequency came from the private, because the FM band was full, and so they wanted new possibility to create new program and have new public. And so that was at the beginning of the 2000, where this ask came. Then a little bit later was the fear of losing a market, and also the influence of the cost of the network cost, how handle, and also the readiness of the network. How much should I put? How much money should I put in the network? How much listener do I have? And this mix. And there in Switzerland, we had the chance that the regulator sustained the migration to DAB+ in giving a little bit subvention on the DAB network. And so this helped the private to have at the beginning the network a little bit less expensive, and so doing this migration.
Thank you.
Okay, I will try to give a partial answer on Italy, which is very different than Switzerland. And we had a scenario where basically DAB was of interest, especially for a group of national operators, which thought that it could be an interesting development for the future and for granting, let's say, independence and let's say, freedom for the media on the long term. And they also wanted to be part of the technological development. The problem was, of course, the Italian FM market is very complex, and I will not illustrate it here because it will take a couple of hours. It was very cool about this. They didn't like it, basically. So what we decided is to create DAB, to implement it and to force them, basically, and to show them it can be done. It can be done at a reasonable cost, and it can be done at also in a relatively short time frame. The time frame in the end was not so short, but the first step we did was we were the first basically to implement DAB+ in Europe, and that allowed us to show that there was capacity on DAB for all the actors, local and national operators, because the change of the scenario was significant. And actually, after a couple of weeks after we started the first DAB+ transmissions, the local associations made a press release in which they said, yeah, no, the future of radio is DAB, which until that moment was something they would not talk about. The second thing we did is to solve the chicken and egg problem with the car industry and the lack of DAB receivers in cars, because it was always the same problem. There are no receivers, there's no coverage. We will not put the receivers on the cars because the customer experience will be bad because there's no coverage. And we said we will not build the coverage because there are no receivers. So we were locked in this situation, and we decided to build the coverage. So we invested for a couple of years into this project, and we demonstrated that we could build a good working network at a reasonable cost. And then we went to the car industry and said, oh, now it's your turn. So that were two steps which were, of course, very important.
So I think maybe from the UK then, obviously the DAB networks have been operational for many years. I think one very healthy thing in the UK is choice. Many of the ensemble multiplexes are full, if or nearly full, and there's great choice in DAB in the UK. And I think combined with that is that coverage is really important. It needs to be reliable, especially for mobile reception. You really want that service to be solid, so that when the car is moving, you get a good service and people get used to it being there. It's reliable, it's on, it's got good choice. I think they're the key things.
Thank you for sharing your experiences in your countries.
Okay, so then I will go on. Are there any questions here from the floor? No. Okay. Then I have a question for Luis for the beginning, which is, you mentioned that you have found in your projects quite different requirements for MER from the different operators. What are these requirements? You have mentioned them partially before, but could you elaborate on this? And how is the tool you have in your transmitters allowing operators to manage this MER?
I think that this has been already a topic we discussed yesterday in the SNIC meeting. Today we have been hearing about this in the GATES-Air presentation, in our presentation, in Phil's presentation. So clearly it's a topic that is an open topic, and each network operator is defining the network in a different way. Probably all of them are right in the way how they do it. Okay, so Phil was presenting very positive results about what is the effect of dropping the MER up to even 20 dBs, and we saw in the video that basically there is no difference. The signal was dropping almost in the same location on the car. Other people are addressing this in a different way. Even there are people who are even trying to optimize the MER of the transmitter by dropping a little bit the power and bringing MERs into higher 30 levels or even 40s. I mean, so the approach is really different. So from our manufacturing point of view, we have no decision on that. The only thing that we can provide is a tool that for them is easy for them to configure the network and the transmitters in the way they prefer. So probably Gateshead has its own tool or way of doing it. In our way of doing it is just through a very simple menu on the interface of the device where you just simply type there the MER you really want the transmitter to operate with. And then internally, based on the number you put there, the power supply is optimized with certain voltages and there, and in the end, you are, let's say, adapting the MER to that value that you put as a target, don't dropping below that one, and optimizing the energy as much as you can. And in the examples we were showing there, I mean, depending on how much is the MER deviation you want to do, but there we were putting an example of dropping the MER 5 dBs and the efficiency was increasing in 3 points or 3 point something. So these 3 points of efficiency improvement in a 5 kilowatt or in a 4 kilowatt or in a 3 kilowatt in a dense network as some networks we have been doing in the last 2 years that we have delivered 60, 70 transmitters of 2 kilowatt for a network, that implies a lot of kilowatts in a 10 years life of a network. Okay, so from our side, what we have to provide is the tool for them to make the network to operate as they want. Then it's a decision of the network operator how they prefer to organize the planning and the MER they need. Okay.
Okay, thank you very much. I have another question which goes to both of the manufacturers in this context. It comes from Phil Brown. So you spoke a lot about Doherty amplifiers. Are there other possibilities which could enable maybe in the future efficiency improvements like a multi-stage Doherty or so-called envelope tracking, if this is suitable, of course, for DAB?
Okay, turned on, yeah. So the answer about multi-stage Doherty is that for real-time adaptive control, it is preferable to have a linear preamplifier and a Doherty final stage. And especially when you're looking at a 2 or 3 kilowatt transmitter, the preamplifier is a 30 watt or a 50 watt low power transmitter. So the effect on the overall power consumption by that small power amplifier is, I wouldn't call it neglectable, but it has very low influence. And the efficiency savings you achieve by multi-stage Doherty are not that significant. Regarding the, what was the other one? The envelope tracking, I am not aware if and what we're doing. So we may need to come back to you on that on a separate line. If you're able to send me an email, I can put you in contact with our development team so to discuss this in more detail. But I understand you're a colleague of Phil's, so yes. 2 Phil's. So I'll discuss it with my people and we can come back to you.
Yeah, same from my side. I mean, we are not for the moment doing any kind of development on envelopment tracking. That's not something that we are doing, at least that I'm aware of. If something there is shown to be significantly more efficient than the existing solution we have, for sure we will follow. I mean, I think that we all concluded this morning that every single item is important. We believe transmitters efficiency is important. Seeing the presentation from Carlo, any single aspect is necessary to be optimized to the maximum. So if we see that there is a technology there that brings higher efficiency into the picture, we will be there, no doubt on that. At the moment, we don't see anything that it really brings more efficiency than probably what we have nowadays. Figures we were showing and the ones that Alex was mentioning in the morning, more or less following the same pattern. Okay, we can be talking about maybe in certain channels you can give a little bit more, a little bit less, but we are always talking about that significant improvement versus probably older devices that are still on the field. And that's the tool that we have nowadays realistically to deploy networks. Other things, if they come and they are better, for sure. Gates and NAS and Rode and everybody should follow. I mean, if they don't follow, maybe they will be left a little bit behind. But we all need to be knowing that our role in this game is to provide the best possible technical solution. This is our part of the game. Other entities need to do other kind of lobbying, pushing, and so on, but we are manufacturers. Our responsibility is to bring the nicer and the more efficient solutions into the networks. Okay.
Okay, thank you, Luis. Very interesting. Phil, I have a lot of questions for you. The first one comes from me because I just went back to the video and I couldn't not notice that you were listening to a station which was broadcasted in DAB because you can hear it on the glitches, which reminds us of a long time ago. Do you think there's a difference between DAB and DAB Plus in the context of the MER reduction?
It's a good question. So we have thought about this. So in the relationship that we showed earlier in effectively the curve in the law, if you like, that we created for the relationship between the change in transmitter MER configuration and the impact on coverage. One of the parameters in there is S upon N. And of course, for DAB and for DAB plus, for both Gaussian and fading channel conditions, you need a different S upon N to protect the service at the edge of coverage. So there is a very small difference between DAB plus and MPEG-1 layer 2 DAB, but those changes are very, very small, less than 0.1 of a dB difference between DAB plus and DAB.
Okay, thank you. Good to know. One more question for you from David, who says, thanks for the presentation, first of all. While typical pattern is to use EEP3A, some broadcasters use different protection parameters, so EEP4A and on the other side 2A or 1A. Can you please comment on the expected impact of the reduction of the transmitter MER for these scenarios?
Yeah, sure. So for all of the information that was presented there in the presentation and the vast majority of the work that we did on the BBC DAB network in the UK, that used UEP3, again, classic MPEG-1 layer 2 DAB. But going back to the point where those different protection layers have got different S upon M requirements, there is a very, very small difference between the impact, the effective loss of coverage from that transmitter as you reduce the MER. So it's about 0.1 dB of a loss for UEP3, and it's within about another 0.1 of a dB or something very, very small between UEP4 and UEP2, for example, and similar for DAB+. So the difference between the configurations of the FEC, which need different S upon Ns, there is a small difference, but it's so small, it's within a 0.1 of a dB again, so it's unmeasurable, I would say.
Okay, thank you. Interesting.
So, sorry, one last thing on that.
Yeah.
So one last thing on that. the Phil Brown, who's just been mentioned, from Arqiva, and Ranulph Paul from BBC R&D, who were the key contributors with myself on this project. I'd say in about a week's time or so, there's going to be a BBC R&D white paper on this topic, and it's going to cover this point off. So you can have more reading at that point.
Very cool. Okay, thank you. A question for Carlo on the other side. You said that to increase the ERP, you have to increase the number of antennas, the size of the feeder line, the efficiency, or reduce the loss of the filter, of course. Do you think it is necessary to do all these things together to avoid the bottleneck, or is there an optimum approach to find, let's say, an equilibrium between costs? Because of course a feeder line can cost, let's say if you go to a 1.58 inch feeder line, it becomes much more expensive. Do you think there is, let's say, a soft area?
Of course, we need the best trade-off between the antenna design and defining all the other items, of course. You say that the right way. Yes, we can add more antennas. This means that we can achieve a narrow elevation pattern. So is necessary add some other activities on the antennas. For example, in some case we need the down tilt within. We have to add the null filling to have the optimum coverage. And in terms of, for example, feeder selection, of course, everything is a compromise between the total length that we have to reach to the antenna. In terms of power, we don't have too much power, so it doesn't make sense go to higher cable or bigger cable. So normally we stay in traditional foam cable around the 7/8 or 1.58. This is, I think, it's the typical approach for the typical power that we have to manage for DAB application.
Okay. Thank you very much. I have a questions for Justice. Do you hear us?
Yes, I can hear you.
Okay, excellent. So the first question, well, which you have partially answered, but maybe you want to elaborate a little bit on this. Why did the government of Ghana decide directly from the beginning to run the DAB test off-grid?
Okay, thank you for this question. Like I said in the presentation, the DTT site was originally installed for it to be powered by solar. So when the government of Ghana decided to conduct this trial, it then decided to use, the DTT sites at least for the trial. And because the DTT site was already being powered by solar, the government of Ghana decided to just upgrade the solar capacity so that it can also power the DAB as well. So this is the basic reason why the government of Ghana decided to power the DAB sites via solar. Thank you.
Okay, thank you. Just a question which comes from the panel here, but I think more or less you answered this. But also the solar panels, therefore you have installed in your sites power the whole transmission side, if we understand this correctly, and not just the ancillary services. So they are able to sustain both the DTT and the DAB transmissions 24 hours a day for the whole year.
Correct, yeah.
Okay, thank you. Thank you very much, Justice. Then let's move on. There were still a lot of questions for Phil. This one comes actually from Alex. Should I turn your question directly? Okay. You spoke about MER optimization without touching the power supply. Could you explain a little bit why? Because usually manufacturers use the power supply to tweak the optimization.
Yeah, sure. So apologies if it came across that we're not touching the power supply. We absolutely are doing the MER optimization with the power supply. We're doing it in conjunction with the modulator because we're controlling the shoulders from the modulator, and we're doing the MER optimization with the power supply. So I think that might be very similar to what you guys might be doing. Does that answer the
Okay.
question? I don't know.
Yeah, and yeah, it sounds very similar to what we are doing.
Okay, cool.
Okay. Oh, yeah. Oh, Stan, go ahead.
Press the button.
It's on. It's on. So I will speak now then. About MER optimization, because it's something, yes, we have on different manufacturer of transmitter on the shelf now. Oh, it's working now. Thank you. And the point is, there is one critical point is the shoulder, because yes, you can reduce your MER, and we see that the impact is not so important for the service area. You could lose a bit of DX, but let's say if you don't focus on that, and usually as an operator, it's not your focus, you can really save energy here. And when you operate, let's say 100 sites over different countries, even if you gain 1.5% on every site, it's a very important numbers at the end of the year. So yes, it is the way to improve efficiency here. But typically here, if I take the example in Switzerland, we are obliged to comply with critical mass. So the minus 57 or 56 dB at plus minus 970 kilohertz from center frequency. Depending how it is implemented, because yes, you can play on the power supply, on the bias, you can play on the pre-distortion, and modulators are software today running on FPGA, so you can do a lot of trick here. You can do software tap filtering, etc. The point is, today my limit for the minimum MER is not in fact what is the impact on my coverage. It's the shoulder I get from the transmitter, because then if you put more energy that you lose in the filter, because when you design the site, it's your antenna gain, your loss of the feeder, your loss on the bridge and the filter. It means it's a complete system. So when you design something in the beginning and I choose finally a brand of transmitter, I take into account their performance on the shoulder. So my point would be that in the future, for future software implementation and hardware implementation, even if you can continue to reduce on your channel your MER, it's really important that the shoulder has a specific mechanism to be controlled, because, and I know it's not easy because you have compromise to do here, but it's where we have the limit today, because we have to comply from the regulator request.
So could I just say that from a network operator point of view, then maybe the manufacturers can talk about it. So I completely agree. So in all of the tests that we've done, now right through to the point where we're now doing the upgrades with an automated approach, what we do, we don't just specify MER and then we hope and expect that the bandpass filter of the combining network will then just help us reach that critical mass, because we obviously have the same thing. We specify the shoulder, minimum shoulder performance. So it's a combination between the power supply, getting you the MER, and then the modulator maintaining the shoulders. So we go for 35 dB shoulders in this particular plus minus 970 kilohertz. And we know in our network that if we're 35 dB or better, and we always try and get better for that MER, then we're going to meet our critical mask. So that's what we're doing. So maybe the manufacturers can tell you how they're doing it. I don't know.
I mean, probably I will put you in contact with more our technical people there, but at least from my perspective, something has been thought about this already, because in the menus that we allow you to play with, you can set up a target of MER or a target of the shoulders. I mean, so basically there you can play with both things and you decide what you really want to play. So that the shoulders are probably as important as the MER value that you need to target there. Okay, so the question clearly has a lot of background meaning behind, and at least in our design that has been already considered as well. Okay.
Okay, thank you. Very interesting contribution. Back to Adriano. You're really wanted. There are two questions on the network. One is on the reception thresholds you plan or you have planned your network in Switzerland, especially for mobile and portable mode. You talked about indoor in your presentation. From the mobile and the portable point of view.
Yeah. So for the mobile, we outdoor we plan with 48 dB microvolt per meter, and for the portable indoor 61 dB microvolt per meter, and in the cities or dense area, then we go up to 71. That's our planning that we. Yeah, that we're looking for the coverage.
Okay, I suppose at 1.5 meters height.
Exactly.
Yeah. Okay. Good. And the other question was, well, it's two questions in one. They come from Mahe. How many different sites are you using now in Italy for? Sorry. Good night. For on Switzerland for your. It's a lapsus. In Switzerland for your DAB network. So you have one national network. For 16 programs, correct? Are they all on the same multiplex?
No, we have 4. In every language region, we have one multiplex. So it's one ensemble per language region, so 4 multiplex. And so in the total for all Switzerland, we have 260 sites, and some sites use provide 2 multiplexes. So in the border area between two multiplexes, but I would say perhaps 10 sites are using both ensemble. So it's quite 250, 240 sites.
Okay.
Physical sites. Yeah.
Okay, no, that's quite a lot. Okay, thank you very much. So we have 50 seconds left. Are there any other questions? I have still a lot of questions here, which I will forward to the speakers. And maybe if you're online and you want to email the project office with your questions, they will try to provide you answers on this. Also, I have to remind everybody, both here in person and online, to complete the feedback form, because WorldDAB, the project office, needs this. If you're like the seminar, you will receive an email from the project office concerning this. And yeah, so that would be all, and we are at 0, so our time is up now. Thank you very much to everybody. Thank you to the panel. It was, I think, really interesting. Thank you for your time, your presentations. Thanks to the attendees here in the room and online. And I hope to see you soon at the next seminar. We will have an online seminar in December and, of course, a seminar next year here, we guess. So thank you very much and goodbye to everybody.